In previous video, we were learning about the storage-based allocation mechanisms, and we have seen static-based allocation and stack-based allocation. In stack-based allocation, in static-based allocation, some absolute addresses were given, and the subroutines that were used, all the subroutines, not only the used one, all the subroutines will be loaded into the memory, which results in wastage. In case of stack-based allocation, what happens is on demand, the subroutines will be loaded to the memory. And it will be making use of the stack pointer and frame pointer. All the subroutines that is being invoked will be having its own activation records, which includes these fields like arguments to call routines, temporaries, local variables, miscellaneous bookkeeping, and the return address. So in which the arguments it comes to the top of the stack, and the others it will be based on the language and the um, system or the hardware in which we are doing the operations. So based on the invoking the subroutines, it will be pushed on to the stack. So it will be following the LIFO principle. And in order to operate on the stack, it makes use of stack pointer and frame pointer, in which stack pointer points to the first unused location on the stack, and frame pointer it points to a non-location, that is a current subroutine. It will be pointing to the current subroutine, the frame within the current subroutine, and it reserves large area for subroutine calls. For each subroutine call, a new frame will be allocated, and once the subroutine finishes its execution, it returns to the calling program. And in such case, what happens is it deallocates the space that is allotted to the subroutine, and it makes use of some memory management algorithm to efficiently manage the memory storage. So this is how it is being arranged. What we have shown in the previous slide, same thing it is being done over here, in which the stack stack will be growing like this, and the addresses also, when as the stack grows, the address also it is decreasing. The address also it gets decreased. This on a subroutine call, what all operations it will be happened. The stack frame will be pushed onto the stack, and the stack frames it differs in size based on the local variables that is used within these subroutines, and recursion only limited by total size of the stack. Reduced weight, that is unused subroutines only consume memory for code and not for the variables. Um, if that is when a subroutine C is being called, these informations will be loaded to the memory, and only this happens when the subroutine C is being called. Subroutine D means what it does is the code alone will be stored. Once it is called, then only these extra variables or information related or the local variables that is being given inside the subroutine will be loaded to the memory. So once it finishes its execution, all those variables will be popped from the stack. Hence, it utilizes the space of the memory. In the calling sequence, compilers generate code to manage the runtime stack, like it makes use of setup, prologue, epilogue, and cleanup. Setup means before call to subroutine, that is setup. Prologue, before subroutine body executes. Prologue. Epilogue, after subroutine body completes the execution, that is the return statement. Cleanup means right after the subroutine call. So these are some of the phases in which a subroutine is being called and subroutine calling instructions takes place. Calling and execution instruction, it takes place in these steps. We are having some um, function declaration, call, and definition, isn't it? So when a function call is being done means first that function gets initialized or will be declared. So some setup will be done before call to the subroutine, like loading the return address and storing the local variables. Those things will be coming to the setup part. Then prologue will be like before subroutine body executes. And some initialization, those things will be coming under this prologue. Epilogue will be like after subroutine body completes its execution, that is moving to the return address. Cleanup is like it has to pop from this, elements need to be popped from the stack. So once the subroutine finishes its execution, it pops all the local variables. It frees the space occupied in the stack, that is cleanup. So, calling sequence, it refers to the combined operation of the caller, the prologue, and the epilogue, in which the caller means it will be having setup and cleanup. Caller will be performing this setup and cleanup. That is, setup is like preparing the arguments, cleanup is like save the return value. Prologue will be a code that is executed at the beginning, like pushing the stack and load arguments. Push to the stack and load the arguments. Epilogue is like code executed at the end, that is set up return value and restore the stack. So the advantages and disadvantages is like negligible in most cases, runtime overhead, limitations. It will be making use of some limited resource. In case of the space, advantage that is being given is efficient use of space, recursion is possible. And the local variable, offset of local variable within frame usually is a constant. That is, we will be able to address the variables from with the help of the frame pointer. You will be able to access the local variables and it will be usually constant. Limitations, in addition to that limited resource, it is stack frame, it is considered to be as a fixed size in most of the languages, and offset computations, it will require some offset computations will be performed at the runtime, and object lifetime limited to one subroutine invocation, and that is when a subroutine is being called, once it finishes its execution, till that time it will be alive. Once it finishes the execution means the object also, it will be that variables and object will be removed from the stack and its lifetime also ends there. So stack allocation, when compared to that of the static allocation, stack allocation is better when compared to static allocation, but the problem arises in case of the larger buffers. So for larger buffers, we go for the heap-based allocation. So from the term itself, heap-based allocation. Heap is a region of storage in which subblocks can be allocated and deallocated at arbitrary times. for dynamically allocated pieces of linked data structures, and for objects like fully general character strings, list, and sets. So heap-based allocation, it will be you will be allocating the memory based on the requirement itself, but it results in what some internal fragmentation and external fragmentation, like mm, that you have seen in the I think you have learned it from the OS itself. Some memory space, some block need to be loaded to the memory, but there won't be some enough space to load that block. That which means some blocks will be there. This example you can see. This is the block in which to be loaded to the memory. So this is the allocated space. These shaded blocks, it seems to be like the used space, and this dash lines, it shows some free space within the block itself, and this will be called as the internal fragmentation. What does that mean? After loading some block into this space, some space was left as free, which results in internal fragmentation. And um, another one case was external fragmentation, in which this block need to be placed onto the memory. There are many available free spaces. This white blocks, it shows the free spaces. Many available free spaces are there, but there is no one such block that is possible to fit this block, that is requested block. Okay, so that results in what? The external fragmentation. So internal fragmentation is like some to some space block will be loaded, but that space was large enough that it resulted in some unused space also. So that is internal fragmentation. Allocates a block that is larger than required to hold a given object. So the extra space, it is left as free. External fragmentation, it occurs when the blocks that have been assigned to active objects are scattered. Okay, so you are having blocks, but it is scattered in the memory, and no one such block is there to fit this um, requested block. Okay, so this, in order to fit this block, you have to identify the free blocks that is available and divide the requested block to those free blocks. So that is what it is, external fragmentation. So in order to fit this block to the memory, what it does, some storage management algorithms will be utilized, such that it will be maintaining some linked list having the free list. So in order to search from the linked list, if a free list means like the free list will be having the set of all free blocks, it ranging from small to large. Uh, so from that set of blocks, it will be identifying. I hope that you are aware of this best fit and first fit algorithms. I think you might have learned in the OS itself, best fit and first fit. What was the difference? In case of first fit, what happens is some list is there which is having the list of all free blocks. In case of first fit, first available free block that is able to accumulate this requested block will be taken without checking the further blocks. And best fit is like it checks all the blocks to see this requested block can be correctly fit. That is less unused space it results. Okay, so such such selection will be such algorithms that is used will be called as the best fit.